Hi there. So this is a video on Module 10 for Math 125, and Module 10 covers sections 11.6 and 11.7, which are on the normal distribution. So we're going to start by talking about the normal distribution, but more specifically, let's just talk about what a distribution is first. So a distribution is just an arrangement of data values. Data values are like numbers that you might collect. Maybe you take a survey and you collect the answers to that survey and you have a data set. An arrangement of data values. You could also think of it as a graph. Okay, so a picture of this arrangement. For example, maybe I surveyed my class and maybe I asked them how many kids they had. So I asked every single person in my class how many children they had, and I got answers like 0 kids, 1 kid, 2 kids, 3 kids. Okay, so on this axis we're going to say kids, and on the y-axis we're going to say frequency, so how many. And let's say, I had this many people say 0 kids, this many people say 1, some people had 2, a couple had 3. Okay, so I have this arrangement of my data. And this arrangement is not normal. It's not a normal distribution. We'll talk about that in a minute, but it's got, it's got a shape to it. Okay. And when you graph data, you'll see that a lot of data actually ends up having a similar shape, which is called a normal distribution. So this example with kids is not a normal distribution, but if I had graphed my data and I had found that I ended up getting a graph that was much more symmetric and looked like we call this bell-shaped. Okay, so if it looks like this, then we call that a normal distribution. So when our data is graphed and it ends up making this curve like this where it's symmetric about the middle, then we call it a normal distribution. And there are many properties of a normal distribution, and there's 7 here listed. Okay, we're going to kind of come back to some of these as we go through the problem. But one thing I want to note first is that a couple of things. Number 2 says the mean, median, mode are all equal and they're located in the center. So the very center of this normal curve, this is where the mean, median, and mode are. Okay, in the center. You can also see by the picture that most of the data values, okay, are around the mean. And I know that because think of a bar graph, okay? So when the bars are the biggest, it means more data values are in that section. So just like in my example over here, the biggest bar is 1. Most students in my class have 1 kid. That represents the biggest bar. So with my bell curve, most of the people are around the middle, and then a few are on the left and a few are on the right. So we have a few outliers on the low end and the high end, but most are around average. Okay, there's a lot of real life examples that can be modeled with normal distribution. For example, ACT scores, SAT scores, male height, female height. You've got most of the population around the middle or the average, and then, a couple people that are on the high end and a couple people are on the low end. Number 7 is also a really important one. Well, number 6 also. So let's talk about 6 first. So the area, okay, under a portion of the normal curve is the percentage in decimal form of the data that falls between the data values that begin and end of that region. So for example, let's actually look down here at this picture that we have. So, and it's labeled empirical rule. So we'll talk about number 6 and empirical rule kind of at the same time. So in the center of this curve, we have the average or the mean, median, and mode. And remember X bar, okay, X bar, we talked about that last module, stands for average. So the mean is in the middle, okay. Every line on this curve, okay, represents standard deviation. So down here where it says X bar minus 1s, it's just saying 1 standard deviation below average. So I like to write it like this. So 1 standard deviation below. And then this line is 2 standard deviations below. And this one is 3 standard deviations below. And then over here is 1 standard deviation above, 2 standard deviations above, and 3 standard deviations above. And if you ever want to know how many or the percentage of data values between certain values on the graph, all you have to do is find the area under the curve. So the empirical rule says that if the data is normally distributed, so it means that the data when graph looks like a bell shape, it will automatically contain these approximate percentages in each section. So let me give you an example that's going to give this some context. So for example, let's talk about male height. Okay, the average male height, and I'm just going to round to make this simple. So the average male height in the United States, so X bar, is 5 foot 9 inches. And the standard deviation for male height is about 3 inches. It's actually 2.8, but I'm going to round to 3 just to make this simple. Okay, let me get a different color so that I can draw these numbers on the graph. So if the average is 5 foot 9, then what we could do is we could put 5 foot 9 right here. Let me get a thicker one. So I'm going to say 5 foot, oh, too thick, foot 9 inches is going to go in the middle. So that's the average height. Now to get one standard deviation above, all I have to do is add 3 because that's the standard deviation. So 5 foot 9 inches plus 3 inches would be 5 foot 12 inches or 6 feet tall. So 6 feet is going to go here. If I add another 3 inches, it's going to be 6 feet 3 inches. If I add another 3, it's 6 foot 6 inches. Okay, so anytime you want to go this way, you're going to add the standard deviation each time, which in this case is 3. To go the other direction, I'm going to subtract 3. So 5 foot 9 minus 3 inches is 5 foot 6 inches. So 5 feet 6 inches. And then subtracting again, 5 foot 3 inches. Subtracting 3 again is 5 feet. So what do these numbers mean? Well, it gives you some context in terms of, you know, if you were a male in the United States and you wanted to know how your height compared to other people, you could look at this curve. So for example, let's say you were a male who was 6 feet tall, which lands you right here. You are 1 standard deviation above average. Using the empirical rule says about 68% of values, okay, so that's what this is down here, around 68% of people fall between 1 standard deviation above and below the mean. So it means you are pretty normal. You're above average, but you're still in the, I would say, the normal range. In contrast, let's say you're a male who is 6 foot 6 inches, where you were 3 standard deviations above. You can see from the graph here that there's just a small little tail, and that represents that very few people are going to be above 6 foot 6 inches tall, very few males. So your height is pretty rare. And the empirical rule says about 99.7% of values fall between 3 standard deviations from the mean. So it means you are outside of that 99.7%, which means your height is pretty rare. So it allows us to determine how many people are in certain ranges, and it also helps us decide whether or not values are normal or rare, depending on the average. So let's use, I'm going to actually erase all this so we can see. We're going to do an example with the empirical rule. Okay. And just to be clear, the empirical rule always works. You can use these percentages anytime the data is normally distributed. So if the data is bell-shaped, you can use these numbers. Okay, so according to the website, the mean height for male humans is 5 feet 9.3 inches. So again, above I approximated 5 feet 9, but we're going to use this exact number for this example. So the average male height is 5 feet 9.3 inches with a standard deviation of 2.8 inches. If this is accurate, out of 1,000 randomly selected men, how many would you expect to be between 5 feet 6.5 inches and 6 feet 0.1 inch? Okay, so let's go ahead and I'm going to draw a picture here. I'm going to draw the normal curve. And I'm going to draw a line in the middle, and that's going to represent the average. And I'm going to put 5 feet 9.3 inches there. That's going to represent the middle. Okay. I'm going to draw bars on either side. So vertical lines, 3 on each side, usually is good. I would say that's the standard way you can draw this curve. Let me try this again. These tails on the side should be a little bit skinnier. Okay, that looks better. Okay, and so this, I'm going to just draw these real quick, just like I did above. If the mean is in the middle, then this would be 1 standard deviation above, or you could say +1, 2 standard deviations above, or +2, 3 standard deviations above. Okay, and then we've got 1 standard deviation below, 2 standard deviations below, and then 3 standard deviations below. Okay, so if we want to know, they're asking us about 5 feet, 6.5 inches. That's less than our average. What I'm going to do is I'm going to use the standard deviation to add and subtract that from 5 foot, 9.3 inches to get our standard deviation numbers on either side of the mean. So I'm going to start with the average. Okay, so I'm going to start with the average that was given, 5 foot, 9.3 inches, and I'm going to add 1 standard deviation. Okay, so I'm going to add 2.8 inches. So what I get, if I add this, is I get 5 feet, 12.1 inches. Well, 12 inches is a foot, so I'm just going to add that here, and that gives me 6 feet, 0.1 inch. Okay, so that's going to be 1 standard deviation above average, and it's above because I'm adding the standard deviation. So let me actually, I'm going to write this a little bit smaller. So this one is 5 foot, 9.3 inches, and then I'm going to take this number and I'm going to put it right there. So 6 feet, 0.1 inch. Okay. The apostrophe means feet. Then I'm going to do 1 standard deviation below average. So I'm going to start with, let me scroll up here. I'm going to start with my X bar. So my X bar is 5 feet, 9.3 inches. That's my average. And now I'm going to subtract the standard deviation. So this is going to be 1 standard deviation below because I'm subtracting. Okay, and then when I subtract those, okay, I end up getting, so if I subtract those, I'm going to have to, I can't do 3 minus 8, so I'm going to borrow here, okay, and then I get 5 point, and then there's a 6, and then I bring down the 5 feet. So 5 feet, 6.5 inches, and that's 1 standard deviation below. That's going to go right here. So 5 feet, 6.5 inches, okay? And that's what I was being asked about. So you'll find a lot of times these beginning problems, the numbers that you're asked about will lie exactly on one of the standard deviation lines. And we want to know how many, okay, how many would you expect to be within that range? So how many would you expect to be within these two numbers? So on the picture, we're looking for this region. We want to know how many are in between those two numbers. And if we look above, if we scroll above here, the empirical rule says that about 68% of values lie between 1 standard deviation below and 1 standard deviation above. And you could also do it by adding 34.1, 34.1, you get about 68. Okay, so the answer here is going to be about 68%. Now you have to be careful and look at what the question is asking specifically, though. Sometimes they ask for percentages and sometimes we want the actual number. So going back to the question, it says how many would you expect? It doesn't say anything about a percent. So this means that we want to know the actual number of people. And if there were 1,000 people selected, then you're going to take 68% of that 1,000. So it's going to be 0.68 times 1,000 people, and that leaves us with 680 men. So there are 680 men out of 1,000 that are going to be between the 5 foot 6.5 inches and 6 feet 0.1 inch. Okay, so the next part, let's talk about the standard normal distribution. So in the example above, we had an average, a male height, and we put that in the middle. We had a standard deviation of 3. Sometimes we don't have those numbers. So what we can use is, it's called the standard normal distribution. And by standard, we're just going to use a standard or a set mean and a set standard deviation. So standard distributions have means that are 0, okay, and you can see this graph is labeled with 0 in the middle, and standard deviations that are 1, okay. And what this does, it helps us answer questions about data sets that, we don't know the specific mean and standard deviation for. So let's talk about z-score. So in our example with male height here, we were asked about heights that lied exactly on one standard deviation below and one standard deviation above, which is convenient. What if, for example, though, I was asking about a male that was 5'8"? So that would be around here, 5'8". That person doesn't lie exactly on one standard deviation. So you could say that person is above average, but you don't know exactly how much above average this person is. So that's where a z-score comes in. So we can find the z-score for this person, and that gives us that exact position of that data value. And there's a formula for z-score. It's pretty simple. There's 3 numbers involved. So, and the formula is right here. You're going to take the data value minus the mean divided by the standard deviation. And this z-score is a measure of position that tells us how many standard deviations a data value lies above positive or below the mean. So just a quick example, let's say the average male height is 5'9", and let's say, I don't know, there was a male that was 5'8", okay? And you wanted to know how many standard deviations away from average. I can tell you right now that this person's z-score, his z-score is going to be negative because he's below average. And we could take that value and plug it in the formula for data value to find the exact z-score. So let's actually go ahead and do that. So let's do this example. So based on the information in the previous example, find a z-score for a man who is 6'4" tall. So I'm just going to write down what we had before. So we had that our average male height, okay, so that's just average, symbol for average, is 5'9.3" tall, and we were told our standard deviation is 2.8 inches. Okay, in the example above, I kept the feet in inches the way they were. I'm actually going to convert these all to inches for this example because that's another good strategy to use if you've got a problem with feet in inches, so I can show you how to do that too. So I'm going to first convert to inches. Okay, so 6'4", that's the number that I was being asked about. There are 12 inches in a foot, so 6 times 12 plus an additional 4 inches gives me 76 inches. So somebody who's 6'4" is 76 inches tall. And then I'm going to convert the average male height, so 5 feet 9.3 inches, 5 times 12, okay, plus 9.3 inches is 69.3 inches. Okay, so that's the average male height, and this is the data value from our example. Okay, so we're going to use the formula. So step 2 is use the formula. We're going to do the data value minus the mean divided by the standard deviation. So our data value is 76 inches minus the mean, which is 69.3, divided by the standard deviation, which is 2.8. And if you calculate all of that, you end up getting 2.3928. It's a big long number. Approximately, let's say we're asked to round to 1 decimal place, you get approximately 2.4. So it means that a male, I'll just draw a picture, so if the average is 69.3 inches and this person is 76 inches, it means his standard deviation is 2.4. It means 2.4 standard deviations above average, which means he's pretty tall. Okay, let's do another example. So one year an ACT had a mean score of 21.2. So I'm just going to jot this down as I read it. So the mean is 21.2 with a standard deviation of 5.1. The same year, the SAT had a mean score of 1050 with a standard deviation of 3.5. 347. Okay, and a scholarship committee is considering two students, one who scored 26, so we'll call this student 1, is 26 on the ACT, and then student 2 who scored 1198 on the SAT. Okay, it's hard to compare these because they're different tests, but what we can do is we can use this information of mean and standard deviation to find out exactly how many standard deviations above or below average they are, and then compare them to one another. So let's just do student 1 first. Okay, so we're going to use the formula. Student 1 took the ACT, so their data value is 26 minus the average for ACT divided by the standard deviation for ACT. And if we work that out, we get approximately 0.94. Okay, this didn't tell us how to round, so I'm just going to round to 2 decimals. And then student 2 on the SAT scored 1198. That's the data value minus the average. Okay, so 1050 divided by 347, and we get 0.4265 dot 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 dot. We round to 2 decimal places, we end up getting 0.43. So in this case, keep in mind that with the standard normal distribution, the average is 0. Okay, so this bottom line, think of this as like a number line. So student 1, okay, is going to be 0.94 above average. So this is number 1. It's 0.94. So it's positive number, so it's above average. To the right is 0. Student 2 is 0.43. So since student 1 is further away from average, student 1 scored better. So we're going to say student 1 scored better. All right, so what we can do here is use, we're going to look at the table from, it's Appendix A in your textbook, to find the area under the standard normal distribution. So for these types of problems in your homework, you're going to be given a link to the standard, the z-score table, which looks like this, okay? And basically what this does is it allows you to look up a z-score. So you can see on the picture this z-score. There's an example here where we've got this line that represents the z-score. The 0 represents the middle or the mean. And if you know the z-score, this table will tell you the area from the middle or the mean going to that z-score. So for all of these types of problems that we're going to do, we're going to first draw a picture and try to figure out, well, where is the area that we're trying to find, and then we're going to use the table to find it. So for this first example, we're going to draw the standard normal curve. You don't have to be perfect. I don't even draw these to scale. Just do your best. We're going to put a 0 in the middle because this is a standard curve. Okay, and then it wants us to find the area between z equals 1.55 and z equals 2.25. Now this bottom line is a number line, so if 0 is in the middle, the number 1.55 is to the right, it's positive. So I'm going to draw a line here and label it 1.55. 2.25 is bigger than that number, so I'm going to go to the right again. Now I don't draw this to scale, I just make sure that I'm going in the right direction. If I want to know the area between those two values, then I'm going to shade the area I want to find. Okay, now on the table, okay, so I'm going to use the table now and I'm going to look up. So I've got a z-score and the table is going to give me an area. Okay, so I've got two z-scores, 1.55 and 2.25. So I'm going to first look up those numbers and then I'm going to draw the picture. So we're going to go to the table and we're going to, let me pull that up. Okay, we're going to go to the, we're going to go to 1.55. So it looks like a z-score 1.55 has an area of 0.439, and then 2.25 has an area of 0.488. Okay, so I'm just going to write those down. Come on. Okay, so 1.55 has an area of 0.439. and 0.488. Okay, so 0.439, remember that the area is always the area from the z-score. So I'm going to use a different color here so we can see it's from the z-score to 0, or from 0 to the z-score. So from 0 to 1.55, the area is 0.439, and then from 0 to 2.25, the area is 0.488. Okay, notice that neither one of these numbers is the blue shaded region, so we're going to have to do a little work here. So if I know that this entire area here is 0.488 and I want this blue section, then I can just remove the section that I don't want. Okay, so I'm going to take 0.488, which is the area of this whole chunk, and subtract 0.439, and that's going to give me the shaded area in blue here. So if I subtract those, I get 0.049, and that gives me the area of the section that I want. If you were asked a percentage, you could find a percentage by moving the decimal 2 spots over and get 0.49%. But it really just depends on what the question is asking. So you have to pay attention to how it's asking the question. So in the next example, so I'm going to draw a curve again. And you'll find that once we get through all of these, we're really going to do one of each type. So hopefully all of your homework problems should relate to one of these pictures, which is nice. So you can go back and use these as an example. So I'm going to put 0 in the middle, negative 0.6. Okay, so it's negative, so I'm going to the left of 0, because negative numbers go to the left, and then negative 1.35 is even more left, and again, these are not to scale. I'm just giving myself lots of room to write, and I went between those two values. Okay, I am going to look up the z-scores on the table and write down the areas for those. So if I look up, okay, this is something to worth mentioning here. When you look up on the table, notice that none of the z-scores are negative. Well, the curve is symmetric. So if you are wanting to find the z-score for negative 0.60, you can just find the z-score for 0.60. So we've got 2.26 for that one. Okay, and then if we look it up for 1.35, see, we're down here, we're at 0.412. Okay. So I'm just going to write those down. So negative 0.60 has an area of 0.226, and negative 1.35 has an area of 0.412. I'm going to draw those on the picture. So starting from 0 going to negative 0.6 is going to be the 0.226. So that's all of this is 0.226. And then starting from 0 going to negative 1.35, this whole region is 0.412. Shouldn't be that extra decimal there. Okay, and so now what I'm going to do is I am going to do what I did in the last example. I'm going to need to subtract, since I wasn't given the area of what I want to find, which is this blue shaded region. So I'm going to take the whole thing, 0.412, and subtract what I don't want, 0.226, to get what I do want, and I end up getting 0.186, which is the area of that red shaded region. Okay, and then let's do part C. So again, I'm going to draw the curve. I put the 0 in the middle. 1.50 is going to go to the right because it's positive. Negative 1.75 goes to the left because it's negative. And I want the area between these two values. Now this is an easier type of problem because let's write down these areas and then we'll see. So we've got our z-scores and then area. So if I look up 1.50, I'm going to get 0.433, and if I look up negative 1.75 or 1.75, I'm going to get 0.460. So if I go ahead and I label my curve, so I've got from here to here is 0.460, and from here to here is 0.433. In this case, I am actually given the areas that I want. So I'm going to add these together in this case. And I would say the most common question that I get on this module is, when do I add, when do I subtract? Well, I guess if you like to follow a certain set of rules, if the z values you're given are if you're being asked to find the area between those two z-values and 0, or the average mean is in the middle, then you are going to add. In the other cases, you subtract. But honestly, I wouldn't even use that like rule so much as just drawing the picture. So make sure you draw a picture for all of these, shade the area that you want, and actually think about how you might calculate that area. And I think that's probably the best way to go about it. All right, so let's do these two, because these we've got some other good ones that have some different types of pictures. Okay, so I'm going to put 0 in the middle. Now we want to the right of 1.70. So I'm going to draw a line to the right, since 1.70 is bigger than 0, and then I want to find the area to the right of that. So I'm going to shade everything to the right of 1.70. Well, if I look up a z-value of 1.70, it's got an area of 0.455. So remember that that's the area starting at 0 going to that z-score. Well, I don't want that. I want this. One thing to remember is that the area under the curve, and actually I may not have mentioned this, but this is a great time to mention it now. The area under the entire curve is 1. And because it's symmetric, you can also say that each half is 0.5, okay? That's given for all standard normal distributions. So if we know that the entire right side of the curve is 0.5, then what we can do is just subtract that 0.455 to find the area that we want. So I'm going to take 0.5 minus 0.455. Okay, we can add zeros there to subtract, or just use a calculator, and then you end up getting 0.4045. And looking at my picture, that's a pretty small area. This is not to scale. I probably should have drawn it more like, this, where the area was just a tiny bit at the end, but that's okay. I think as long as you draw the picture, it'll help you find the answer, as long as you just remember that your picture is not drawn to scale, unless you want to try to draw it to scale. Okay, so the next one, I'm going to put 0 in the middle. We've got a negative z-value, so I'm going to the left of 0, so negative 0.95, and we want to the right of that. So that means all of this, and we're not stopping at 0, we're going all the way to the right. Okay, so remember from the last example that the entire right-hand side of the curve and the left, this is all 0.5. So if I can figure out what this is here, then I am all set to go. And I can by looking that up in the table. So if I look a z-value of 0.95 up in the table, I end up getting an area of 0.329. That's going to be this number. So it's going to be starting at 0, going to negative 0.95. So I'm going to add those two numbers together. So 0.329 plus 0.500, or 0.5, and I end up getting 0.829 for my area. Okay. Now I've got two more like this, and I know this might seem like a lot, but I'm trying to go through all of the different types of pictures you might see, so that way you can have an example of everything. So 0's in the middle, we've got a negative z-value, so I'm going to the left, negative 2.20, and I want to the left of that, so I'm trying to find this area. Well, if I use the table, I can look up 2.20 and find that the area starting at 0 going to that z-score is 0.486. So if this area is 0.486 and I know the entire right hand side is 0.50 or 0.5, then I want to, in this case, I'm going to have to subtract. I'm going to take 0.50, which is the entire left side of the curve, and I'm going to subtract 0.486 because that's what I don't want. I want the blue area, not the red, and then I get 0.014, which is my answer. Okay, so last one. So I'm going to draw a curve, get pretty good at these curves when you do them enough. Put 0 in the middle, 1.95 is going to go to the right. Okay, and I want to the left of that line, so that means I want all of this. Now, right away, just like in the last example, if I'm trying to find an area where half of the curve is included, in this case, I'm going to say that that's 0.50, so I know that. Okay, the table, if I look up 1.95 in the table, it's going to give me the area starting at 0, going to 1.95, and that area is 0.474. Okay, so I am actually going to add those two numbers together. So I'm going to take 0.5 and add 0.474 and get 0.974, okay, which is 97.4%. So the majority of the data values are going to be in that range. Okay, so that was all of the first section, 11.6. Now 11.7 is application. So how does this help us answer questions in real life? So let's just jump in. So in this example, just like before, I'm going to draw the normal curve. In this case, it's not going to be the standard normal curve. It's just going to be the normal curve. So I'm not going to put a 0 in the middle. If the weights of Oreos in a package are normally distributed, so that basically tells us we can draw this curve with a mean of 570 or 518 grams, so I put that in the middle, and a standard deviation of 4 grams, find the percentage of packages that will weigh less than 510. Okay, so what I would do at this point is draw some vertical lines on either side of the middle and use the standard deviation, add it and subtract it to the middle to find the values that should be on those bars. I'm just erasing the G there so I have more room to write. So what I mean by that is take the average, 518, and add 4 to it. Okay, so and then take 515 and subtract 4. Okay, so I end up getting 522 on the right, and then if I subtract 4, I get 510 on the left. And you can keep going on either side if you want, but really just look at what the question's asking, and as long as you end up finding the value that they're asking about, you don't have to go any further. So in this case, we want to know how many packages will weigh less than 510. Well, I just found that 510 number, so I don't actually have to keep going to the right. I don't even need to go to the left anymore either. I found the number that I want. So 510, I'm just going to draw that in a different color, is right here. And we want to know how many packages are less than that, which means all of this area. Okay, and we've got 518. Okay, that's our average. That's our middle here. All right, so I'm going to use the I'm going to want to use the table, okay, but the problem is the table only gives us z-scores and area, and I don't have any z-scores. So what I'm going to have to do, step one is draw the picture, okay. Step 2 is going to be to find the z-score for 510. So I'm going to use the formula data value 510 minus the mean 518 divided by the standard deviation, which is 4, and I get a z-score of -2. So I'm going to look up 2 on the table, and that gives me a z-score of 0.477. So that means that this area starting at the middle going to that z-score is 0.477. And so if I want to find the area shaded in red, I'm going to have to take the whole left side, which is 0.5. Okay, so now I'm on step 3. I'm going to take 0.5 and I'm going to subtract the area that I don't want to get the area that I do want. Okay, so 0.023, and it's asking for the percentage, so I'm going to take that decimal and move it 2 spots to the right and get 2.3%. Okay, so this next problem, you notice I've got this note in bold here that the area underneath the curve is the same thing as the probability that a data value is going to be in that region. So we're going to use that with this next example since it's asking for probability. Okay, so we've got some data here. I'm going to draw a curve, and this would be a great place to pause the video, try to draw the curve yourself, and then come back. So it says that based on 2009 data, the average American generates 1,679 pounds of garbage per year. So that's our average. I'm going to draw a line in the middle. So 1,679 pounds of garbage, that's the average. Let's assume that the number of pounds generated per person is approximately normally distributed. So that means we can draw this curve and use our table. And it has a standard deviation of 200 pounds. Okay, find the probability that a person generates between 1,300 and 2,000 pounds. So you're going to need to figure out where are those on the table. Now, if 1679 is in the middle, 1,300, that's less than that. Okay, so why don't we just draw some lines to the left? I might as well just draw the ones to the right too while I'm at it. I'm going to use my standard deviation to get some values to the right and to the left. So if I take 1679 and I subtract 200, let's see, I'm going to get 1679, and I'm going to subtract 200, and I end up getting 1479. Okay, and then if I subtract 200 again, I end up getting 1279. Now you'll notice 1300 doesn't lie on those standard deviation lines. It's somewhere between 1279 and 1479. So I'm going to say 1300 is about right here. So I'm going to actually have to use the z-score formula since it's not an exact standard deviation. So I'm going to use the z-score formula here and use my data value 1300 minus the mean divided by the standard deviation, and I'm going to round to the nearest tenth. I get about negative 1.9. Okay, and so what I could do at this point, I'm going to actually draw this curve over again since those standard deviations that I originally calculated weren't the numbers that the problem was asking for. So I'm going to put 1679 in the middle, 1300 on the left, and 2000 on the right. Okay, we found the z-score for 1300 is negative 1.9. Let's find the z-score for 2000. So 2000 minus 1679 divided by 200, we end up getting an approximate z-score if we round to the nearest tenth of 1.6. Okay, so that's above average. We want to know what's the probability of being between those two values. So at this point, what we're going to do is we're going to look up on our table. We're going to look up 1.6 on our table, okay, which is this value, and that gives us an area of 0.445. And then we're going to look up 1.9 on the table, and that gives us an area of 0.471. We want to know the probability between that range, so all of those shaded regions. So I'm going to add them together. Okay, so step 1 was to draw the picture. Step 2 was to find the z-scores. Step 3 is to look up the areas on the table. Okay, and then step 4 is going to be to add those together, and I end up getting 0.916. And you could leave it like that, or if it asks for percentage, then you could move the decimal and get 91.6%. Okay, so let's go ahead and do the next example. It's going to be really similar to the last one, just the picture is going to look a little bit different. So we're going to draw the normal curve. We're going to put our average garbage in the middle. This asks for more than 2,000 pounds, the probability. So 2,000 is bigger than 1697. I'm going to draw a line there, and I'm going to shade to the right since more than is to the right. Okay, so I want to know what that area is. In order to find the area, okay, so step 1 was to draw the picture. Step 2 is going to find the z-score of 2,000. Well, I already know the z-score for 2,000. So the z-score for 2,000, we did it above here, is 1.6. So I'm going to look up on the table, which I did before. So step 3, find the area. So the area for 1.6 is 0.445, and that's the area. Get a different color here. That's the area starting at 0 going to that z-score. So 0.445 is all of this. Okay, but I want that blue area. So I know that the entire right-hand side of the curve is 0.5. So step 4 is just going to be to take 0.5 and subtract 0.445, and I get 0.055. Okay, and then if I want a percentage, I can move the decimal 2 spots to the right, and I get 5.5%. So 5.5% of people produce more than 2,000 pounds of garbage per year. So this is how we can use these scores in areas under the curve to actually answer questions that apply to real life. So pretty interesting. All right, so let's look at this next example. So we've got American Automobile Association. Reports the average time it takes to respond to an emergency call is 25 minutes. Assume the response is approximately normally distributed. So I'm going to draw a normal curve. and I'm going to put my average is 25 minutes in the middle. Standard deviation is 4.5. If 80 calls are selected at random, approximately how many, so I'm not finding a percentage, I'm finding the actual number, have response times less than 15 minutes. So 15 minutes, if 25 minutes is average, 15 minutes is going to be less than average. And I want to know how many will have response times less than that. So I'm going to shade everything to the left of 15 minutes. I can't look 15 minutes up on the z-score table, so I have to find the z-score for 15 minutes. So 15 minus the average divided by the standard deviation, and I get approximately negative 2.2. We're rounding to the tenths place because that's the number, that's how the table works. I'm going to look 2.2 up on the table and find that that has an area of 0.486. Okay, that's the area starting at 0, going to, or starting at the middle, the average 25 going to 15. So this average is 0.486. Okay, I want this shaded region here. So to find that, I know that the entire right hand side of the curve is 0.5, that area. So I'm going to take 0.5 and I'm going to subtract 0.486, and that's going to give me 0.014, okay, which is like 1.4%. Now in this case, we want to know how many people are going to have response times less than 15 minutes. So if there are 80 calls, I'm going to have to take that decimal and multiply it by 80 to figure out the actual number of calls. So I end up getting 1.12, and if this were a connect problem, it would likely have you round to the nearest whole number. Since 1.12 calls, that doesn't make any sense. So I'd say about one call in 80 will have a response time less than 15 minutes. Okay, so this next one asks about a percentile. So remember from module 9, we talked about percentiles. Percentile is just the percentage below a particular value. So let me just draw a picture here. We've got our mean response time of 25 minutes in the middle. In what percentile, or what's the percentage below of a response time of 30 minutes? So 30 minutes is going to be to the right of 25. Just going to erase that by room. And if I want the percentage below, I want all of this, okay? Now I know that 0.50 is the area of everything to the left of the average. I need to know what's the area between 25 and 30. So that area right here, I'm going to use the chart, okay, in Appendix A, and I'm going to find the z-score for 30. So 30 minus the average divided by the standard deviation, 4.5, is equal to 1.1 about. If I look 1.1 up on the table, I end up getting an area of 0.364. So this area is 0.364. And then if I want all of that, so I want the 0.50 and the 0.364, I'm going to add those together. So the total area is 0.500 plus 0.364 equals 0.864, okay? So therefore, okay, so the symbol means therefore, a time of 30 minutes corresponds to the 86th percentile. So 0.864 is about 86.4%, okay? And usually with percentiles, we just round to the nearest whole number, but in Connect, when you're doing your homework, you'll be directed on how to round, okay? So when in doubt, with all of these questions, I want you to draw your normal curve. You put your average in the middle. If you are given an application problem where you're given a mean that's not 0, you're going to have to calculate the z-score first before you use the table. If you're given a problem where the average is 0 and you're actually given z-scores, then those are a little bit simpler. I'm just scrolling up here to show you. So like these problems here, you don't have to find the z-scores, they're given, then you just go ahead and use the table. And again, the table should be given to you. There's a link within your problem, and you can also access it by going to Appendix A in your textbook.